Good afternoon, everyone. Um, I'm Devesh Ranjan from School of Mechanical Engineering at Georgia Tech. And on the behalf of the organizing committee, let me welcome all of you to the second week of the Frontier series. And we have a very exciting program for the whole semester. For today, our theme is Wearable Robotics. And the session will be moderated by Professor Marcia O'Malley from Rice University. And the speaker for today, we have Professor Elliott Rouse from Michigan and Aaron Young from Georgia Tech. So let me go ahead and just introduce our moderator for today, and then I'll pass the ball for her to moderate the session and introduce the speaker. So Professor O'Malley is the Thomas Michael Panos Family Professor in Mechanical Engineering, Computer Science and Electrical Engineering at Rice University. She received her bachelor's in mechanical engineering from Purdue and her master's and PhD in mechanical engineering from Vanderbilt University. So Marcia is very well known for her works in haptics and robotics rehabilitation with a focus on design and control of wearable robotics. She is fellow of different societies, so there's a lot of difference. So she's a fellow of IEEE, ASME, and has been the co-editor-in-chief of IEEE Transaction on Haptics. So with that, I'd like to thank Marcia for the help here, and doing this, Marcia, you can take the ball and it's all yours. Thank you.
Well, thanks for the opportunity to introduce our speakers today. I'm going to actually start by just introducing the topic very, very briefly. So let me get the right buttons clicked here. Nope, share the wrong one. Try again. We practice this. There we go. So you should be looking at a cartoon. So wearable robotics is a really fast-growing field, and I just wanted to give you the scope of this field and the kinds of problems that people are working on. So wearable robotics are really interesting devices that have close physical interactions with humans, and many of the applications are sort of related to human movement and biomechanics and rehabilitation. You might be familiar with exoskeletons that are intended to assist with loss of function, or prosthetic devices that replace lost limbs. Or even now, there's a lot of investigation into exoskeletal devices that can protect people from injury. And an exciting kind of offshoot of wearable robotics is the idea that not only can we restore function to those who've lost it, but we might also be able to enhance normal function. So there's also the development of exoskeletons to do that, and development of supernumerary limbs and fingers. So, you know, why not give ourselves extra limbs and extra fingers to help us with our tasks? So we're going to be diving into just a subset of this area of wearable robotics today with our two speakers. So I'm really excited to introduce both Elliott and Aaron. So Elliott Rouse from the University of Michigan and Aaron Young from Georgia Tech. Both of these gentlemen are focused on the design and control of wearable prosthetic and orthotic devices for the lower limb. So let me just briefly introduce each of them. The Big Ten is strong here today. So Elliott is an assistant professor in the Department of Mechanical Engineering at Michigan and a core faculty member in the Robotics Institute. He directs the Neurobionics Lab. His degrees are at Ohio State and Northwestern. He did a postdoc at MIT and was the winner of the NSF Career Award. I asked both Elliott and Aaron to share with me what they think are some of the challenges in the field of wearable robotics. And Elliott said he's excited about how we might develop better ways to quantify success of wearable robots beyond the usual quantification of metabolic cost. And in fact, it's recently shown that people are quite insensitive to metabolic rate, which makes that metric less than ideal for a measure of success. And a fun fact about Elliott is that he left his previous career as a mechanic for a professional auto racing team because he wanted his work to have greater impact on people with disabilities. We are also both from Ohio, so that's another fun little fact. Aaron, our second speaker for today, Aaron Young, is an assistant professor in the Woodruff School of Mechanical Engineering at Georgia Tech. He directs the Exoskeleton and Prosthetic Intelligent Controls Lab, or EPIC Lab. We are fellow Boilermakers, and he got his master's and PhD in biomedical engineering at Northwestern. He postdoced at Michigan, and he recently received the NIH New Investigator Award and the IEEE New Faces of Engineering Award. Aaron articulated a challenge in the field of wearable robotics as generalizing wearable robotic devices across the wide range of things that humans do every day in their home and community, while also still personalizing these devices to individual needs and attributes. And a fun fact about Aaron is that he did his PhD in the same lab as his randomly assigned co-presenter, Elliott. They both worked in the Center for Bionic Medicine at Rehab Institute of Chicago, now the Shirley Ryan Ability Lab under Todd Kuyken. So with that, I will pass the baton to our first speaker for today, Elliott.
Thank you very much, Marcy. Let me share my screen, make sure that this works. Can you see my screen?
Yes.
Okay, thank you again, Marcy. I'd like to talk to you today about reverse engineering the human neuromotor system and the kind of role of these properties in the design and control of wearable robots. As a disclaimer, the variable stiffness ankle that I'll talk about in this presentation has been licensed for commercial use, and I am an inventor on the pending patents. I'd like to make this thing go away. Can you see this little window? Can you see an extra window from the call on the screen or no? Okay, good.
No.
Okay, great. So the human neuromotor system is capable of amazing things. And we do this through strength and coordination and training and skill. And in a video I like to highlight that kind of shows these capabilities. Here's a professional snowboarder kind of interacting with the environment on their snowboard. And you can really tell that this person is an expert at controlling their limbs, and particularly the kind of mechanical interface between their legs and the snowboard and the ground. So these training and skill really translates to advances in motor performance. So that's the ability to regulate our joint torques or our kinetics, the ability to regulate our kinematics or body pose information, and then a concept called mechanical impedance, which is kind of the stiffness properties of the body, which I'll talk about for just a second. So mechanical impedance is really the instantaneous relationship between a perturbation displacement and the applied torque. We have lots of different mathematical forms to represent this, the most common being a second-order mechanical system consisting of inertia, damping, and stiffness. In the human body, we can regulate these properties using muscle coactivation. So muscles can only pull. So to provide motion and torque in 2 dimensions, we have agonist and antagonist musculoskeletal architecture. So by flexing these 2 muscles together, we can change the stiffness without changing the net torque or the joint's position. So we actually have independent regulation of kinetics, kinematics, in this concept, mechanical impedance. And this isn't just like a theoretical or mathematical property. This property really matters to locomotion. It describes how energy would be stored and exchanged between the joints of the leg and how disturbances go from the center of mass or from the ground to the center of mass. And these are properties that are critical for efficient, stable, and agile locomotion. We often, as roboticists, go back to biology as a blueprint for design and control. And we've really seen some amazing advancements kind of in this space. An example, agility robotics by Professor Jonathan Hurst, the Cassie robot. I believe in wearable robotics, bio-inspired dynamics could lead to kind of more natural response to disturbances, a more intuitive human-machine coupling, getting away from the feeling of sort of riding the technology that you're wearing, and really ultimately exploitation of the advanced capabilities of the human neuromotor system. So in the field of wearable robotics, we get our biologically inspired instructions by looking at tasks in 2 dimensions. We look at torques and angles and how these properties vary throughout a task. Here's an example of the ankle joint during walking. This will come up later in the talk. But this kind of 2-dimensional set of information is what we would use to design a bio-inspired system. And if we think about what system dynamics or what stiffness should the system have to replicate biology, for the past probably 100 years of biomechanics, people would take the slope of this torque angle curve, and it has the right units, kind of Newton meters per radian or Newton meters per degree, and they would call that the stiffness. So it would be like something like this. But as it turns out, that's not true. That's sort of mathematically inappropriate. When muscles are doing work on the body, you can't just take the slope of this curve. Stiffness is a separate property. And some work I did earlier in my career kind of made this point. So really, I'd say like one of the overarching goals of my research program is to translate this two-dimensional information of kind of torques and angles to a new type of blueprint, a three-dimensional set of instructions, where we can vary and control not only the torques and angles, but also the joint stiffness information. And I would call this probably one of the fundamental goals of my research program is quantifying and understanding these properties, both in context of wearable robotics, but also in the context of neuromotor control. And my hope is that we can leverage this information as a new blueprint for the design and control of assistive technology. And I'm going to talk about kind of this set of information in this talk. So the first thing I'd like to describe is how might we get mechanical impedance as a blueprint. Over the last 6 years, we've been working on these methods, and this is the same torque angle relationship of the ankle. And every step, you kind of go around this cycle. And to understand the stiffness or mechanical impedance properties, we really have to interact with the limb or apply perturbations. And our approach has been to apply perturbations at kind of discrete points within the gait cycle that give us kind of snapshots of how these properties vary. And if we stack these snapshots up in time or in phase, we can get an idea for how the neuromuscular system is regulating these properties. So we've been developing these methods. This is an example of our kind of experimental paradigm. Someone walks across a walkway and they experience a slight perturbation, about 2 degrees. And that blue thing in that video is a force platform. So we measure the force between the foot and the ground. And then we can fit a model, a second order mechanical model between the perturbation displacement and the perturbation response torque. And we do that using system identification techniques. So what I'd like to show you now is some of the data that we've published recently. So in this plot, we're looking at stiffness as a function of percent stance phase. In the light blue, we show data from running. And in the dark blue, we show data from walking. And the data that is particularly the new data on the walking study was the last 2 points. So what's happening during terminal stance phase. And what we showed is that the stiffness is actually much higher in the ankle joint during running, and then it has a similar profile where it increases, and then it begins to decrease in terminal stance phase, which occurs a little bit earlier in running biomechanics. And if we look at damping, we see also much different responses, and this is also consistent with the literature that the stiffness and damping, or the damping during running, would be much higher because the muscle activation is greater, and damping is known to co-vary with muscle activation. One of the exciting things I'd kind of like to highlight just for a second is that we've also been thinking about extending these methods to quantifying pathological impairments. So if you have an upper motor neuron disease like stroke or cerebral palsy, that manifests itself in changes in coordination and joint mechanics, and that inhibits mobility and makes it much more difficult for people to walk. These changes that occur, they would call in the clinic, they would call it spasticity and hypertonia, but in mechanical engineering, we would call that stiffness and damping. So we can get a kind of a insight into the changes that occur following a stroke by actually measuring the mechanical impedance as people walk. These are some data from a recent study we just completed. We're again looking at stiffness as a function of stance phase, but in this case, the lines represent, the dark blue line represents the non-paretic side of a person who's had a stroke. The light blue part is their paretic side or affected side. And then the gray is older, healthy subjects that are age and speed matched. And what we see is that the stiffness of their non-paretic side is actually much greater, and the stiffness of their paretic side is consistent with age and speed matched controls. For damping, we actually see kind of no changes or no increases in data that's consistent with the age speed match controls. And this really, I think, highlights an important point about treatment of spasticity and hypertonicity in people with stroke or cerebral palsy, where they get this information, these changes to joint mechanics, while people are seated and a therapist or clinician interacts with their joints and subjectively scores it while they're at rest on a measure between 0 and 4. And those measurements would, in the history of the literature, would say that we should see an increased stiffness and an increased damping on the paretic side, but we actually don't see that. We see no increase in damping at all and no increase in stiffness on the affected side, where we do see a large increase on the non-affected side. And I think that's likely due, the large high stiffness on the non-paretic side is likely due to the greater activation of the harder they're working on their non-paretic side to help push themselves forward during the gait cycle. So I think these data really begin to highlight that we need a new way to quantify and assess the changes that occur post-stroke so that we can appropriately treat these patients. So going back to kind of this idea of stiffness, kind of torque and angle as a set of instructions, we can take these data from the able-bodied testing I showed first and really create this kind of 3D set of instructions. And that's what's plotted in this plot. We're looking at torque, angle, and stiffness, all co-varying during the walking gait cycle. And I'm hoping to use this as this new blueprint for design and control. And then what I'd like to talk about for the next few minutes is how we have translated this into wearable robotics. What we showed is that for the first 2/3 of the gait cycle or stance phase, a passive system can actually replicate the mechanics of the ankle. So we've designed a quasi-passive ankle foot prosthesis that can actually replicate torque, angle, and stiffness at once up until the powered kind of part of the gait cycle. So I'll tell you about this variable stiffness prosthetic foot that we've developed. So this is our technology. We call it the variable stiffness prosthetic ankle foot, or the VISPA foot for short. It has a couple innovations that I want to draw your attention to. The transmission in this system is cam-based, which allows us to specify the exact torque angle mechanics that we want. We're not confined to the mechanics of carbon fiber leaf springs that would be consistent with today's conventional prosthetic feet. So when someone rotates their ankle joint, it deflects that spring and we store and return energy. And like I said, we can kind of shape this torque angle biomechanics in any way that we want, which is kind of a special property of this prosthesis. The next innovation I'd like to draw your attention to is that we can change the stiffness of this foot by changing the support condition of this cantilever spring. So essentially that means we can take our custom torque angle curve and basically rotate it around the origin by modifying the support condition. So we would adjust the stiffness step to step so while the foot is unloaded. And I think this is kind of among the first variable stiffness ankle prostheses that have been developed. And another innovative design has been developed by Peter Adamczyk at Wisconsin. It's worth looking into. This is just a video of somebody walking with the system. So you'll see they store energy at heel contact, then they dissipate energy and then store it again over controlled dorsiflexion. They push off with the energy that's been stored. And you can, if you look very closely, you can see a slight underdamped response from the ankle, which just comes from its efficiency. So we used our torque angle curve to create the appropriate mechanics that would be following torque, angle, and stiffness at once for the first 2/3 of stance phase. And we tested this on the subject. So you're looking at a single subject's kinematics as a function of percent stance phase for 2 different activities. And the different lines here represent different slider positions or different stiffness configurations. And what I'd like to highlight is that we were able to vary kinematics by changing ankle stiffness, and that we were able to show a much more natural agreement with the range of motion of healthy biomechanics, in part because we can make this foot much less stiff than conventional prostheses, which are quite stiff and have a very constrained range of motion. Something I'm excited about that I mentioned earlier is that we're translating this out of the lab and it's being commercialized by a company called Willowwood. And I'm very excited to see this kind of potentially impact the lives of patients, hopefully in the next few years. So what I'd like to do now is kind of shift gears a little bit and tell you a little bit about how we've used this new system, this variable stiffness foot, to address some pretty neat questions, I think, in preference-based control. So we're going to talk about user preference now and wearable robotics. So the modern rationale for design and control of wearable robotics consists of really like 2 philosophies, I'd say. The first is kind of expert tuned based on biomechanics. So the objective here, like we've talked about in the first part of this talk, the objective here is to replicate kinetics and kinematics. There's also a relatively new philosophy called human-in-the-loop optimization, where instead of using an expert to tune based on biomechanics, the controller is tuned automatically based on a physiological objective function, which is often metabolic cost. So people are trying to tune, or really the system is really tuning itself to reduce the metabolic cost of the wear. And there've been some very successful studies that have come out with this approach. But in my research group, one of the things that we think about is that people's objectives likely change over time and with different activities. It's not likely that there's one objective that's going to meet the needs for every person in every activity. In fact, people probably care about a host of different things: balance, comfort, pain, stability, effort, and the exact emphasis they might place on any one of these different items might depend on the person or the task. So one of our kind of approaches we've been exploring is the idea to use user preference as a way to gauge what the person actually wants, as sort of using all of these factors at once and letting the subject really kind of tune their own system. So what I'd like to do for kind of the next 15 minutes is tell you about 4 kind of project vignettes. So these are questions that we've been answering recently. So the first question that I'd like to discuss is, what ankle foot stiffness do people actually want? We don't know that, and in part because we never had a system that could change its properties step to step. So let's start by figuring out, what do people actually care about? The next question we asked is, how does user preference differ from clinician preference? Then we looked at what underlying mechanisms may drive preference. So what might people be sensing that's kind of governing their response? And maybe can we use this information in the future to guide the design and control of these systems? And then finally, I'll switch gears a little bit and tell you some of our more recent work on preference-based control of ankle exoskeletons. The first question we wanted to answer is, what stiffness do people actually want? So we created a CAM profile for our variable stiffness foot that was linear. So I'm showing the torque angle curve here. So it's a simple torsion spring. And people have access to change the stiffness of their foot by controlling a dial that's mounted to their waist. So as they adjust the dial, we adjust the stiffness automatically as the foot's in swing phase between their steps. We had people walk on a treadmill. We had them find their preferred stiffness using the dial and kind of explore the space. Then we stop the treadmill, randomly reseat the dial, and start over again. And we did this 5 times to not only get an estimate of what stiffness people prefer, but what is the distribution of that, or the variance associated with it. And the data looks something like this. So we're looking at preferred stiffness here for each subject. There's 2 things that I'd like to draw your attention to. The first is, people are very consistent. The coefficient of variation here is 14%. So people are actually surprisingly reliable when selecting their preferred stiffness. The next thing I'd like to point out is that people have pretty different stiffnesses by varying up to a factor of 3 or 4. And all of these subjects had about the same activity level and about the same body mass. And that means when they go to the clinic, if they went to the same clinician, they'd all get fit with the same prosthesis. But yet each person has a different preference. And in fact, these preferences span by quite a large amount. So I think this has kind of important implications in the future prescription of prostheses. And the takeaway here at this point is that people are sensitive, consistent, and diverse in the selection of their stiffness preferences. The next question we answered is, how does user preference vary from clinician preference? So this is an interesting study paradigm where we had 7 prosthetists observe 7 people with amputation during walking. Not every prosthetist observed every patient. So we had a group of prosthetists observe a single patient, and we repeated that for all subjects. Subjects walked across a walkway in front of prosthetists 39 times at 13 different stiffness values. And then each prosthetist indicated, based on observation of the person's gait, whether they think the stiffness should be increased or decreased. And then similarly, the experimental subject with amputation also noted to the experimenter whether they would like the prosthesis stiffness to increase or decrease. We use these data to create psychometric functions that describe consistency and preference associated with stiffness. I'm not going to share those exact functions and psychometric curves just because they take some time to unpack. but I have them in backup slides if anybody's interested to see them. This is an example of what the study looks like. So here's the prosthetist observing the patient. And if you look in the kind of back left corner, you see my former student, Max Shepard, who just graduated and is now actually working with Aaron Young and Greg Sawicki at Georgia Tech. These are the data from this study. So on the y-axis here, we have the percent difference of the stiffness from the below-knee amputee's preference. So we're looking at, 40 here would say that the prosthetist preferred a 40% stiffer prosthesis compared to the patient. Each color here denotes a different prosthetist. And there's a few things that matter about this plot, but I really want to just draw your attention to one thing, given time constraints. It's that prosthetists prefer, on average, a much stiffer prosthetic foot, about 26% stiffer. And this did vary between clinicians and subjects, or as a function of those, but that's really important, that subjects have a preference that's much less than prosthetists. The reason why prosthetists probably prefer much stiffer feet is because that's the way feet are built today. These carbon fiber conventional prosthetic feet are quite stiff, and they're likely informed by the biomechanics that they've been seeing throughout their careers, and now sort of converge to a stiffness that's much stiffer than maybe what people actually want. The last project in this kind of series I want to tell you about is maybe what's driving preference. What are people sensing that's actually informing them of their preferences, given that they're so reliable? For this experiment, we measured 3 people that walked at fractions of their preferred stiffness. So we found their preferred stiffness, we had them walk on a treadmill, and then we had them walk at stiffness values that were plus and minus 15% and plus and minus 30% away from their preference. And we did this across 3 different speeds. We measured metabolic rate and full biomechanics using instrumented treadmill and motion capture. And we looked at how do these kinematic and metabolic factors vary with stiffness. These are the data from this. I'd like to kind of walk you through these plots from left to right. On the left-hand side, what we're showing is metabolic cost as a function of ankle stiffness, which is percent deviation from preferred. So 0 represents the subject's preferred stiffness, and then we see plus and minus 15 and plus and minus 30%. So if we look at metabolic cost, what we see is really no relationship associated with stiffness. The different colors here represent different walking speed. We see a clear trend with walking speed, but we actually don't see any trend with stiffness. So people don't seem to be selecting their stiffness based on their metabolism. In the center plot, we have peak knee flexion moment on the sound side. And what we see here is a linear relationship, which also suggests that nothing is really being optimized here. So if they wanted less or greater knee flexion moment, they would move to one of the extremes, either less stiff or more stiff. So no discernible optimum shown. But then what we did see, looking at the plot on the far right, is we're looking at cross ankle angle root mean squared error as a function of stiffness deviation. And what we see is a second order relationship, or a parabolic relationship, that has its vertex within, has a 95% confidence interval that includes their preference. So it looks like potentially what people are actually feeling that might be guiding their preferences is their kinematic symmetry. They want stiffness values that maximize the symmetry between their prosthetic side and their sound side. And that's a really exciting result. So the takeaways for this section of the talk are that prosthesis users prefer a much less stiff foot than what is available. Prosthesis users have diverse and consistent preferences. Prosthetists prefer a much stiffer foot. This is more like what's available today. Users are far more consistent than clinicians in the selection of their preferences, and that stems from these psychophysical curves that I can talk about in the future. And people may prefer stiffness values that improves their kinematic symmetry at the ankle joint, and that could have potentially far-reaching effects for design and assessment of these technologies. Now I'd like to take this kind of one step further and talk a little bit about a pilot study we've been doing on preference-based control of exoskeletons. So exoskeletons are also very challenging to design, tune, and control, just like prostheses. And we've been looking at an approach to control bilateral ankle exoskeletons by letting subjects kind of self-tune. And we selecting the controllers based on their preference. So the goal for the study was really to determine the controller preferences for people wearing an exoskeleton, And we looked at how these preferences change across speed. This is a pilot study, so 2 subjects, they were able to self-tune their exoskeleton. And the exoskeleton that we used was something called the Defy ExoBoot from this startup company. Defy's exoskeleton uses brushless motors, the T-Motor U8. It has a weight of about 1.35 kilograms. It's a unidirectional actuator, so it only can provide a planar flexive torque. And it has a nonlinear transmission ratio that varies between 4:1 and 17:1, depending on angle. The way that we parameterize the torque that's being provided by the exoskeleton is using peak torque timing and peak torque magnitude. So this plot shows an example of the assistance that would be provided by the exoskeleton. And this really mimics the kind of push-off phase of the gait cycle where the calf muscle is contracting and the exoskeleton is going to help push them forward. We built this into a 2-dimensional touchscreen. Here you see it on a little screen. Now we have it on a large tablet. And when subjects select on the screen, it maps their selection in 2 dimensions to these different profiles, peak torque magnitude, peak torque timing, and an example of the profiles are shown on the screen. And we asked them to explore the space and find the settings that they liked. On this plot here, you can see the x-axis is peak torque timing, y-axis is peak torque magnitude, and you can see where they started. They sort of explored the different control parameters and then found where they liked, kind of up in the upper right-hand corner. And we repeated this again 4 to 5 times and at 3 speeds. And we get data that look like this. Here's our 2 subjects. X-axis is, again, peak torque timing, y-axis is peak torque magnitude. And we're plotting their response. We fit a multivariate Gaussian to their data. The colors here represent the different speeds. And if we look at their profiles as a function of gait cycle, we can kind of see the differences in the profiles that they preferred across the different speeds. And there's a couple things that kind of stand out. One thing that's important is that the people's timing preferences were very consistent, both across speeds and in between subjects. But their magnitude preferences were very different. So one subject 1, preferred less effort from the exoskeleton, even though they could have more or less effort if they chose to. And then subject 2 preferred much more assistance. So it kind of gets back to this, there isn't kind of maybe one size fits all. So the summary for this kind of initial study in exoskeletons is that people are able to reliably tune their own exoskeletons in 2 dimensions. Users have distinct preferences for peak torque amplitude, and really no discernible trend was observed with speed, although this is just our first 2 pilot subjects. So future work will be investigating the sensitivity and underlying mechanisms that drive preference, and similar to how we've been investigating that in our prosthetic work. So I'd like to take maybe the last 3 minutes and just tell you a little bit about our open source robotic leg. Control is one of the greatest, in my opinion, one of the greatest challenges to the widespread adoption of robotic legs. In my mind, it's why you don't see robotic legs in the public. It's very difficult to control these systems reliably and safely. And if they make a mistake, it can cause a very serious injury to the wearer. Fortunately, we have many talented researchers around the world studying the control strategies to help advance these systems out of the lab. But before someone can study their control strategies, they have to build a robotic leg. So that's inefficient because now everyone is reinventing the wheel. It costs hundreds of thousands of dollars to build one of these legs, and our community is spending this over and over and over again. And it also hinders comparisons. So it makes it difficult when people publish results to separate the impact of the hardware versus the impact of the control strategy. So our goal here was to develop an open source platform to kind of unite this field on a common hardware system on which to test their control strategies. This is our open source leg. It's a modular 2-degree of freedom system, so it can be used as an ankle or knee or both. If we look under the hood, we can see the internals here. We use motors that were developed by the drone industry that have higher torque and they're more efficient. The high torque that they provide really opens some doors in terms of design. We're able to get a lower transmission ratio, about 50:1, which is something like 3 to 6 times lower than what's used in conventional prostheses. We use belt drive transmissions because we have such a low transmission ratio. And we chose belt drives because they're quiet, efficient, and low cost. So they don't have long lead times associated with different manufacturers of precision machine components. We also integrated different sensing modalities into the robotic leg, including a 6-axis force torque sensor that's shown here. But there's also IMUs, there's motor current voltage, there's encoders at the joints and at the motors. And it's fully self-contained, so we want to encourage people to get out of the lab and test in the real world. So each system has an onboard battery and control embedded systems. And finally, the knee contains kind of a neat technical modification called a selectable series elastic actuator, which I'm going to skip in this talk, but I'd be happy to talk to anybody if they'd like to connect about it later. If we kind of, that's what it looks like back with its clothes on. And if we, this is just a quick video I wanted to show kind of us testing in our lab with our open source leg. Here, this system is being controlled by a $20 Raspberry Pi. And we've developed a set of open source Python APIs that can enable people to get up and running very, very quickly. So all of the integration between the software on the microcontroller and the brushless drive, all of that has been extracted, and it's just simple function calls. I'd like to point you to the open source leg website, opensourceleg.com. We have everything on this website that you would need to manufacture this and assemble it and control it. So we have solid model files, bill of materials, quotes, sample emails, assembly, detailed assembly instructions, detailed control instructions, software, open source data, sort of everything you need to get going. And again, the idea here was that we would be developing a platform for the research community, and I'm really excited to share that we have right now, we have 8 to 9 institutions that are either using this or are building it as we speak, including Professor Aaron Young from Georgia Tech. So I just want to close with this video. This video is highlights some of the work of our collaborator, Professor Levi Hargrove, but it just kind of, I think, shows what this leg was intended for and its capabilities, and really that we're trying to kind of get this technology out of the lab and into people's lives. This is Terry. Terry lost his leg in a motorcycle accident, and he's been helping us develop this robotic leg through collaborations for the last 3 years. So thank you. With that, I just want to close and thank my students who produced this work, my sponsors, our funding agencies, and then showcase the new robotics building that's about to open up. I will be sharing a brand new lab with Professor Robert Gregg, and I am very excited to open that building, and I hope you come check it out. Thank you.
Thank you, Elliott. So we'll have the Q&A session after Aaron's talk. So Aaron, you can take the ball.
Great. Okay, can you see and hear me okay?
Yes.
Awesome. All right, thanks for having me here. I just want to start out by saying thanks to Devesh Ranjan for really, doing a lot of work to get this seminar series going and inviting us here today, and also to Marcia for introducing us and moderating the session. So I'll be talking today about personalizing control of robotic prostheses and exoskeletons through new advances to intent recognition systems. And so I run the EPIC lab at Georgia Tech, and we really focus on the science of wearable robotic systems, and specifically how control systems interact with human biomechanics. And we really are looking at this for improving community ambulation in a range of different clinical applications, where we're using both robotic exoskeletons and prostheses, and you'll see examples from both throughout the talk. And so one of the big groups that you've already kind of seen presented on that has significant clinical impact with these technology is lower limb amputees, of which there's over 150,000 major lower limb amputations that happen in the US each year. And this does lead to a limited community ambulation capability, increased metabolic costs, and importantly, chronic joint pain and disorders associated with the amputation. So they're left with a significant deficit. And the current standard of care is really passive prostheses, and for neurologically impaired individuals like stroke survivors, typically ankle foot orthoses are prescribed. And these passive devices leave patients with significant mechanical deficits, such as what you can see on the right, an amputee walking with a passive device. And so what has been really exciting in the field is over the last 5 years, companies and labs have really developed a lot of new robotic technology to potentially restore or augment human locomotion performance. I'm showing sort of the main devices that are now out there commercially. And Elliott alluded to this too, but besides just the weight and the cost associated with these, there's one of the main reasons that these devices aren't being used ubiquity is that the control is very complex and difficult and very hard to generalize to a wide variety of contexts. But when you talk to patients, one of the main motivations for wanting a robotic device is the ability to do lots of different tasks well. And that's one of the really cool parts about having a robotic prosthesis. As you can see in this video, it restores potentially the capability of being able to do ramps and stairs naturally and be able to go down ramps and stairs. And so really the ability of these robotic devices to change the sort of the control strategy and morph to help out with a lot of different states is a really important advantage of robotic exoskeletons and prostheses. But to do this, it requires really smart and advanced control systems. And at least in my lab group, we typically divide the control between sort of 3 different fundamental layers. One of these is kind of the high-level controller, which primarily does what is called state estimation. And so this may be, for example, the different locomotion modes that you just saw in the video. But then these states are then mapped to commanded joint torques in a robot through some sort of mid-level controller. And I'm showing the example of an impedance controller, which is great since Elliott just kind of talked a lot about impedance, and often that's used as a control system, which relates kind of these states to commanded joint torques. And then at the low level is a more classical controls paradigm in which the robotic torque is matched to the commanded torque through some sort of closed loop feedback control. And my group really studies both the high and mid-level control, but since this is kind of a shortened talk, I'm really just going to focus today on the high-level control aspect, which is really the state estimation. And so in order to do this, my group has developed a lot of different hardware that we've created in-house in Wearable Robotics, and this kind of showcases some of our different applications. On the left, you can see some of our hip exoskeleton work with the target population of post-stroke survivors. And then in the middle, this is the prostheses. There's a knee ankle prosthesis. This is the OSL that we developed in collaboration with Elliott's group at Michigan. And again, a target population of above knee amputees for the prosthesis work. We also do work with knee exoskeletons for cerebral palsy patients, where we're working on rehab therapies in that group to improve their motor functions. And finally, a back exosuit, and Marcia actually touched on this, for industrial applications for workers who have significant manual materials handling jobs that lead to back problems and injuries. So there's a wide range of different use of cases for this wearable robotic technology that we're excited about. And having these devices really allows us to kind of study the science of how control affects human biomechanics in each of these different groups. So to kind of get started with this, I kind of want to introduce the idea of what are sort of the important human states that a wearable robot might care about or be able to interact with. I think one of these is user intent. So trying to understand, what does the human user want to do? Do they want to speed up or slow down or even change their mode of walking or to running or transition to a stair step, for example, are all good examples of potential user intent. Another important thing to potentially for the wearable robot is the environmental state. So are they walking on rough terrain or level or unlevel terrain? These types of things all might affect how the controller might assist the human user. And then finally, kind of another potential capability that these devices have is to really understand and monitor the underlying physiological state of the user. And so this may be looking at underlying muscles or joint loads, the idea of monitoring fatigue or excess joint load, and potentially intervening appropriately to provide increased safety and enhancement to human users. So I'm going to kind of walk through these. We do work in all 3 of these areas. but I'll kind of start on our work on intent recognition. And one of the ways that we've typically thought about intent recognition is sort of transitioning between a lot of different locomotion modes, which is something we do every day in normal community ambulation, which is something that we really care about. And even just going, from one class to another for a university student, you might transition between these different states 10 different times. And the idea is we really want wearable robots to be able to accurately have a way of seamlessly, naturally, and automatically transitioning between all of these different states for the human user. And one of the main technologies that we've looked at to do this is something known as sensor fusion. So the idea is we can take sensors from the robotic device itself, so these might include joint encoders, load cells, IMUs, and other mechanical sensors, and fuse these with wearable sensors that we might place on the human user that can give us an additional set of information. And one of these wearable sensors that we've especially spent some time looking at is EMG, or electromyography. And this is really recording the electrical potential of muscles through surface electrodes. And this can give us kind of a feed-forward window into the neural control of the human user, which can be really potentially valuable for human intent recognition. And so all of these can be combined or fused through a machine learning system. And so this is a typical pipeline that my lab group might use for these machine learning applications, where we take a lot of different sensors, we do some basic signal processing on those, and then we extract out statistical features through the sensor fusion algorithm. And these different features are then fed to usually some sort of machine learning classifier. This could be a neural network or a linear discriminant analysis. And that classifier will rank order those different classes and produce a likelihood of how likely the user is in any of those given classes. And that likelihood information is often fed to something like a dynamic Bayesian network, which I think is really important for gait applications, where the sequential modeling of gait, or basically the time history, is incorporated into the decision through something known as a transitional probability matrix, which encodes the probability of transitioning between each of your given states. And this allows for a smooth output of the user locomotion mode. And these things include things like sitting, level walking, ramps, and stairs. And so basically, once we get a bunch of training data from a user, for example, with a prosthesis doing these different tasks, we can then start looking at sort of interesting questions like, does adding this EMG information make a significant difference? And so this is one of our earlier results of looking at, okay, the general hypothesis is, well, we have the robotic sensors in the device. So really, how valuable is it to add EMG information in addition to those mechanical sensors? And our typical way of quantifying this is through the classification error of the algorithm on withheld testing data. And so what we did was run a sequential forward feature selection search, where we're adding sort of the most valuable EMG channel at a time and looking at impact to classification error. Over on the left here, this is transitional classification error, so error that occurs on transitions from one step to another. You can see as we add EMG, that tends to decrease the error rate even all the way up to 9 channels of EMG added. And in terms of steady state classification error, so this is on non-transition steps, adding the EMG information does improve the classification error at least up to about 4. And overall, EMG improved the intent recognition error rate by reducing about 1/3 of the errors compared to a robotic suite only. So this was, I think, a cool early result, but we can even take this a step forward and implement these into online systems, which is some of our work that we published in JAMA a few years back. And so this shows EMG being generated in real time and a machine learning classifier that's automatically switching the amputee between going up the stairs or being able to go down the ramp, where all he has to do is think about going up the stairs or down the ramp, and it automatically and seamlessly switches between all these different locomotion kind of modes that you see in the video using this machine learning system. And another cool thing that we can do with EMG is run like a pattern recognition algorithm, where we can take those patterns and allow him to have direct control of the knee or the ankle, at least while he's sitting. And so these are some of the really cool capabilities that these high-level controllers can give us. And you can see, one of the things that we did was take this amputee up 103 floors of the Sears Tower with this system, which is kind of exciting, showing that these things can kind of work out in the real world. And so I think this potentially is a good advancement for wearable robotics with the ability of allowing these systems to modulate better community ambulation. But there are still some significant challenges and reasons to why this technology is not yet deployed. And a couple of them that our group has been tackling that I'm going to kind of talk about today is first that the system is very discretized, which is not necessarily representative of real world ambulation. So the current system that you just saw sort of just outputs level walking, or you're taking a step up a ramp. But in the real world, people want to walk at a lot of different speeds or on different incline angles or ground inclination angles. And these systems don't do a great job of generalizing to the wide variety of contexts that actually exist in the real world. So there's a big challenge there of how to generalize to real community ambulation. And another big challenge that the field faces is that most of the systems presented are user dependent. And what I mean by that is that it requires a lot of user specific training data to get such a good system like what you just saw in the video, where that amputee may have trained that system for about an hour before we got a really nice system performance. And a big question is, how can we generalize these systems to a novel patient that will have a unique gait pattern and not enforce a large training regime, which is not going to be practical in clinical settings. And so creating user-independent systems is sort of a big open-ended question. So in order for us to sort of tackle this problem, our group has really invested in sort of two different technologies and the fusion of those, which is big data and artificial intelligence, which are sort of hot topics in the field of robotics in general, but represent some pretty exciting potential advances. And so in terms of big data, this is not only collecting data from lots of different users. Ideally, we would love to send devices out in the real world, but for now, it's collecting from a lot of different users in the lab, but also from a wide range of different contexts. So across a wide variety of stairs and ramps and all these different things that we typically encounter. The idea is getting tons of data, and if sort of Facebook and Google and these other companies have taught us anything, it's really getting to sort of do well at this game. You need a lot of really high quality data in order to allow artificial intelligence algorithms to really begin to reason more like humans and have sort of the natural and intuitive responses that we expect that they might have. And that requires a ton of data. And it also requires really smart algorithms that can leverage that data. And one of those that's now really hot in the field is deep learning. So the idea of really advanced networks that can learn from these huge sets of data and do some really interesting things. And we'll talk kind of about both of these. So first, to get started, some of the stuff that we've been doing on more of the data-ended side is really trying to simulate in the lab real community ambulation, where we include transitions between lots of different states, but also changing the environmental state. So in the bottom left, you can see in this video kind of changing incline angle continuously, as well as stair height, or collecting data at lots of different speeds on the treadmill. We've done these protocols like what you can see in the video with amputees, as well as exoskeleton users, and on a wide variety of just able-bodied control subjects to get some of these large data sets in which we can relate wearable sensors to human motion intent. And one of these data sets I'm kind of happy to share that we've recently submitted. This is work by Jonathan Camargo, one of the students in my lab, includes 22 subjects. This is an able-bodied kind of control subject group in which we've collected EMG from all the major lower limb muscles, as well as motion capture data. So that's the kinematics that you see here, as well as kinetics, so joint torques and joint powers, along with a huge set of wearable sensors. So IMUs at all the major limb joints and electrogoniometers and FSRs. And with all this data, we can potentially really look at how these different sensors applicable for different types of devices can relate to human motion intent. And we're sharing this as an open source data set for the field if people are interested to be able to run different algorithms on a huge data set. And we're working on generating this on prosthesis and exoskeleton users too. And with this, what we've done is develop kind of a new part of the pipeline to our standard machine learning system, which involves an environmental parameter regressor. So this new component allows for kind of continuous state identification of the environment. So now a system can say, not only are you going up a ramp, or you're about to take a step up a ramp, but that ramp is a 10-degree incline or a 5-degree incline, and we can then smoothly scale the assistance on a device appropriately. And so this is, a pretty nice advancement in terms of the ability of devices to recognize human motion intent and environmental state. Here's a case example on stair locomotion. So with stairs, we can divide this into a classification task of, are you trying to go up a stair step or on the level? And you can see kind of the standard classifier will do a really good job during steady state. During the transition, there is some error where it might think you're a little bit early or a little bit late, but then usually it gets it pretty quickly and converges to very close to 100% accuracy. But what we've added here is also the ability not only to recognize that they're trying to do those stair steps, but what is the height of those stairs. So in this case, we varied stair height from 10 centimeters all the way to about 20 centimeters. And you can see that in the light blue, our estimation, our regression, our machine learning regressor estimation of that stair height, which has an associated error of about 1.3 centimeters, which we think is pretty good for being able to scale assistance based on what basically the incline angle of your stairs are. And so what we've done is taken this a step further and looked at how does this affect human biomechanics on the stairs. So in this case example, what we're doing is comparing an active prosthetic to a passive device. And what we're doing is one of the big differences, if you kind of look at the biomechanics, is on the powered device, we're delivering an early stance knee extension moment, which allows for a step over step stair ascent gait, which isn't possible on most passive prostheses. And what I think is fairly exciting is if you just look at a basic outcome metric, which is just how fast can they go up the stairs, they're able to go up, or they choose to go up faster with the active prosthesis compared to the passive prosthesis. So this is in steps per minute. So 19 with the passive versus 28 with the active. So still a lot slower than what able-bodied people would go upstairs at, which at least we were clocking in at about 50 in terms of self-selected speed. But what is exciting about the prosthesis is that it also improves the efficiency. So it reduced the total mechanical energy requirements by about 37%. And this is kind of shown or designated by the size of these pie charts. The area of the pie chart shows the total mechanical energy. And what is important is because we're delivering additional mechanical energy on the powered prosthesis side, the amputees actually reduced how much mechanical energy that the knee on the intact side had to do. And you can see these reductions from here to here in the pie chart. It's actually corresponding to 5 times less energy needed in the intact knee for a powered prosthesis user compared to a passive. And that, I think, is pretty exciting for potentially reducing kind of the loading on that joint, which we know is excessive and leads to long-term degradation of their intact joints. So that's, I think, a really cool advancement of what some of these powered prostheses controllers are capable of doing. We've also extended this paradigm to ramps. So this is just kind of showing our quick case example on ramps. Here you can see tracking of one of these machine learning systems during a typical ambulation circuit. And you can see a little bit of delay with it going on the ramp, and that's corresponding to about 60 milliseconds of delay, which we think is pretty darn good for a machine learning system to be able to recognize not only are you on a ramp, but that ramp is 10 degrees of incline. And you can see even a harder task down here where we're actually tracking dynamic slopes, so you can vary the treadmill continuously in terms of slope, and then look at machine learning tracking during those slopes, even at different speeds. Our tracking error is about 1 to 1.5 degrees. And this is work that Jairo, a PhD student in my lab, has been working on. And it's actually a fully user-independent system. So basically what that means is we're taking a big pool of subjects, training the data from that group of subjects, and then testing on a withheld user. And that allows us to track for a novel user their ground estimation or their ground slope estimation. And we think that this is pretty good tracking error that at least for a user independent problem, ground slope seems to be fairly reasonable. Another area that we've done a lot of work to kind of extend these systems to allow for continuous state estimation is in walking speed. So trying to understand how fast someone wants to walk. Do they want to speed up? Do they want to slow down? This is work that Christian Bachta in my lab has done. He's a PhD student. And we, in terms of user-dependent walking speed, so we're using training data from the user, we can do this pretty well at about 0.05 meters per second in error. And you can see kind of the tracking performance here from 0.5 to 1.5 meters per second. And one of the things that I thought was really interesting from some of the work that he's done is that at a good point to why these machine learning systems are not perfect is that they do a great job of interpolating, but they tend to not extrapolate. And what I mean, extrapolate, which what I mean by that is if you take one of the training points or one of the speeds and remove that from the training data that you give to the machine learning algorithm, but then test on it, it generally does a great job of recognizing as long as you withhold that sort of within the realm of the training data. And that's demonstrated by how well our tracking is. You basically want it to fall along this blue line, which is the ideal response. But as soon as you withhold data from one of these edge conditions from the machine learning system, you can see that it really doesn't generalize or extrapolate at all to the correct speed. And so this is one of the important paradigms is with these really big data sets, we really need it to incorporate the total range in this example of walking speeds that somebody might want to walk at, or else the system's really going to fail to generalize. And another result over here is for a user-independent system. So what we also wanted to do was similar to the ramp incline problem, was generalize this across multiple users by training on one big user group and then testing on a withheld user. And even with sort of the very most advanced deep learning systems that our group is working with, which is convolutional neural networks and long short-term memory, or LSTM networks, we're only getting estimation error around 0.1 meters per second, which is not wonderful tracking. And this is basically double the error compared to the user-dependent systems. So at least in this case, the simple way of maybe doing user-independent regression really didn't work very well. And it really isn't just for the speed problem. We kind of see this across multiple other problems. If we look at the classic locomotion mode classification error problem, we can look at independent systems compared to dependent. And this is work that Christian recently published in RAL. And it was about double the error of the independent system for both transitional and steady state error. And also in gate phase estimation error, which is something very common to the wearable robotics field, where we try to track where you're at in the gait cycle, we get a lot higher error with an independent compared to a dependent system. So this is a little bit disappointing in that just large data sets sort of didn't allow us to really get awesome accuracies across different tasks. And so what we've done is trying to come up with some new clever ways in terms to address this problem on the algorithmic side. And so what I'm going to show here is some of our initial results with real-time adaptive machine learning systems, specifically an example of a convolutional neural network. And this is work that Insum Kang and Pratik Kunapali in my lab have really worked on that I think is exciting. And so in this case, we're using a deep learning system. And to me, one of the main things that makes a deep learner really a deep learner is that it's actually learning the feature representation of the data. So rather than sending in hand-engineered features, basically it's learning what the feature representation of the data should be. And this requires to do it well, it requires a huge data set, which usually means across a lot of different users, a lot of experiments, and a ton of training time on a lot of computers to create a really good static layer or a convolutional layer that's meaningful. But what we can do, and so this really is not fit well to real-time adaptation, but what we can do is potentially adapt what's called the dense layer, or the dense layers of these deep learning systems. And the way in which we can do that is by taking data that people generate and sending it to so this middle module allows for sort of real-time, very fast prediction of, in this case, gait phase and speed as forward predictors. So we're trying to predict speed and the gait phase of the user and on a hip exoskeleton. And what the slow layer does here is it tries to learn what the labels should have been on the data. So we can send the data back in a queue and look at estimating what the person actually tried to do. So what was the correct speed and what was the gait phase by reconstructing it either using IMUs or a separate machine learning system. And then on a Jetson Nano, we can basically real-time adapt or update the model weights of the deep learner by backpropagating the dense layer. And so this kind of offers a way in which in real time, we can adapt the system to a novel user's gait biomechanics. So they may walk a little bit different than everybody else. And the idea is we can adapt to them over time, which I think is a really cool prospect. And here's some of our initial results with these systems.
Aaron, can you wrap it up in 5 minutes?
Yep, I'll be done in 5 minutes. Yeah, so on the right, you can see both the speed and the gait phase adaptation. The static model is in blue, so this is the fully user-independent model, and as it doesn't necessarily get better over time, but the adapted model does get better over time, and in about 2 or 3 minutes of walking, actually converges to what the user-dependent rate is. And so this is a pretty exciting way of potentially allowing for systems to be deployed and adapt in real time with users and their unique gait patterns without requiring lots of patient-specific training data. Okay, so the very last thing before I kind of wrap up here is kind of taking this whole deep learning paradigm even a step further. And this is work that Dean Molinaro and my group has really been piloting. I think is a very interesting alternative approach to our more classical controls way of running wearable robots. And the idea here is to take a lot of different data from different users and sensor data across a wide range of different tasks and try to relate that to their underlying physiological torques. So we're measuring all this data and measuring their biomechanics as well and using deep learning paradigms to try to relate all this sensor data to their underlying physiological torques, where we could use that potentially to control an exoskeleton. So in this case, this has all work been done at the hip, in which we're looking at hip joint signals and relating that to hip joint torque using a deep learning paradigm. And what we found so far is that these machine learning systems can beat sort of a classical system, which would be just providing a biological torque to a user that's representative or some percentage of their biological torque during different modes. So that could be level ground walking, ramp ascent, or ramp descent. And what the deep learning systems are able to do is give this more accurately. And what that means is that they're providing sort of that step-to-step variability in torque is being registered to some extent with the deep learning paradigms. And then what's especially cool about something like an LSTM is that it can learn to do this more like the biology. And so the way in which I'm kind of showing this, you can measure this formally through a measure of smoothness here and show that the total variance error is lower. But if you just look at the torque plots of tracking torque, the yellow is sort of the ground truth. That's what we're trying to track. That's the underlying biological torque of the user. The LSTM tracks it not only more accurately, but in kind of a smooth biological looking fashion compared to like a standard neural network. And so this is potentially a way in which we can control a device without necessarily doing a lot of state estimation or mid-level control by trying to sort of just deep learn what the user torque should be. And so this is a quick example of this where we're kind of estimating the biological torque with a hip exoskeleton in real time. And this is being augmented by more of this classical classifier that's identifying the intent of the system and can be sent to the deep learning to enhance its ability to recognize different nodes. And so this is kind of, I think, a cool new type of approach that some of my lab members are looking into that presents an alternative to more of the classical controls paradigm that is used in the field. Okay, with that, I will wrap up and take any questions. Thanks to all my collaborators and many student contributors and our funding sources that supported all these projects. Thank you.
Thank you, Aaron. So it looks like Elliott was already answering the question on the chat. So if you have question for Aaron right now, because Elliott has just answered most of the question, if not all of them. Aaron, one of the question is, can't you estimate user intent using perception system? Using a camera, and ANN can predict what mode of locomotion the user is going to employ.
Yeah, that's a great question. So machine vision, and I think a few groups in the field have really been looking into that. Helen Huang's group, for example, have been using a laser sensor to do depth perception. I think that that is a potential alternative approach compared to wearable sensors. What's a little bit difficult about it, of course, is now you have to add this camera to it, and typical machine vision systems require very intense, large processors that need to be on there to really utilize those properties. So it's definitely a lot of hardware and additional computational power that you're going to have to add. And we certainly hope to be able to do a lot of these problems without necessarily adding cameras. The other big challenge to cameras is a lot of times we can get it set up and work really well in the lab, but as soon as you go to different lighting conditions that the system hasn't been trained for, it can be extraordinarily difficult and things don't generalize. And that's something that I think many people in the robotics field have to deal with, but makes it especially challenging to wearable robotics applications.
There was just a clarification question about labels. Labels, ramp walking, a level walking, etc. Don't a priori in your work. Can you hear me, Aaron?
Could you repeat the question? Sorry, I didn't get it.
So these was about your ramp walking. So are the labels and as well as level. So are these levels known already a priori in your system?
Are the labels known a priori?
Yeah.
No, I think the answer is well, I mean, I guess yes and no. I mean, the system doesn't know the range necessarily, but sort of, because the training data incorporates those levels. I think the answer that the person is looking for is yes. The system, we do, in the training data, all of it is a supervised problem, which means labels are provided during that training. So in the training part, that it does know what those labels are.
I was just trying to clarify. I was wondering if you, this was my question that apparently was more complicated than I thought. I was just sort of wondering if you had thought about, there are some methods out there where you can sort of characterize your system based on take a model-free approach, characterize it, and then do a segmentation of the different models that you fit to it to come up with sort of to not really know ahead of time even how many labels you're going to look for in your data.
Yeah, that's more of, I think, a unsupervised learning approach, which some people have looked at. I think generally we found that is a lot more challenging to get to work. I think that it requires, it's simply a lot harder to run unsupervised problems in general than supervised, is going to be my quick answer. But I'm happy to talk more details about it later. I mean, we and others have looked at some unsupervised problems. It's just really hard to get those to be at the fidelity or anywhere close to the fidelity of the supervised problems.
Other question for you, Aaron, is you could use the EMG signals to control the foot leg while sitting down. Is there a limitation to the EMG system while standing and walking?
Yes, definitely. I mean, I would say we are generally not comfortable to giving people direct modulation of control with their EMG during walking. And I would even argue that patients probably don't really want that. Thinking about or trying to control specific joint motion is not what the human neural system does during walking. I think that from a neural control perspective, there's a sort of a regular gait pattern that our nervous system typically runs, and we're sort of not thinking about exactly how every joint is coordinating. And so in a similar way with robotic prostheses controllers, we typically run some sort of controller that just allows for regularized walking during almost all the locomotion tasks. And the EMG at most might enhance some of those tasks, like allow you to modulate maybe the amount of push-off that you're getting, or the amount of assistance you're getting during knee assist or during stair set, but not necessarily regulating each joint individually with EMG control, like we do with upper limb prostheses, or while an amputee is sitting and can just freeform control their prosthesis with EMG.
The other question is about the error. So during the transitional state, you have said that you have a larger error compared to the steady state. Is that because of relative data size, or what are the other constraints there?
Yeah, it's definitely just harder to recognize that somebody wants to transition, and I think that those states tend to look a lot like the previous locomotion mode. So I think I'm still presenting this. This kind of shows that as a grid case example for stairs. You can just see that the classifier here, this sort of shaded, shows that it's an early misclassification, right? It thinks it's going to go into stairs a little bit too early. Here it's showing that it hasn't, right? That's the error associated with it, a late misclassification. And this is just generally true. It's hard to get that timing sort of exactly right. And so you incur errors on that transition step due to primarily misclassifications between the upcoming state and the previous state. And that's really kind of hard to really bring down too much. But we can create fairly smooth control systems that allow for some fuzziness of error during the transitions that still allow for very smooth kind of or fairly seamless walking. Hopefully
Thank you.
Yeah.
So Elliott, I think you've already answered all the questions, but can you summarize some of these questions and maybe in 30 seconds, just give a brief pitch of a couple of questions?
You want me to summarize the questions that got asked and answered?
Yeah, a couple of them. So not all
Sure.
of them, but for the audience who cannot read them.
Yeah, so Hyunwei Lee asked if we'd looked at kind of weight-bearing asymmetry as a potential explanation for the high stiffness on the non-paretic side. And that was a really good point. So we haven't looked at that. We do have a force platform only on one of the legs, but maybe stroke subjects oftentimes bear weight on their sound side more than their affected side, and maybe that's potentially contributing to the increase in stiffness. So that was really great. Greg Sawicki asked, do we think that there's maybe difference in preferred settings for each exoskeleton operating in a different joint? So this would be like maybe people care about peak timing for their ankle, but maybe they care about a different factor for their knee, and have we like explored that, and how might we handle that? And the answer to that is we haven't yet explored different joints. So we've only been working with the ankle at this time, but I do think what I'd like to see in our approach is that it's not confined to even 1 or 2 dimensions, and that we're actually able to tune multiple dimensions at once. And we're kind of working on approaches to make that possible. So then it might be people are able to consume or tune very large dimensional controllers, emphasizing the aspects of that controller that they find most important.
Thank you, Elliott. And I think I just saw a hand raised. So I think there was a last question, which I'll just take. It's about what do you both think are the next big question?
So maybe like I can go first. So what is the question is, what is the next big push in the field of wearable robotics? So we actually like had this meeting earlier in the week where we talked about new metrics for quantifying success of exoskeletons, but that's something that like I'm like especially passionate about at the moment. I don't think we have good enough metrics of success, and we've really focused on a couple or one specifically. And I think the overemphasis on any single metric for application of exoskeletons, which have such broad implications in mobility, is potentially a challenge for the field. And what I want to see is new metrics being developed by us and our colleagues that propose metrics that really evaluate other aspects of exoskeleton use and how they impact people in the real world. So metrics that are accessible and convenient to measure so that we can kind of get these technologies out of the lab and into people's lives.
Aaron?
Yeah, that's great, and I agree with Elliott. We helped host this session earlier. I think following on to that of sort of the theme of how things can affect people in their daily lives. I think one of the big questions is definitely how people will actually use these devices out in the real world, what they end up wanting, and where our systems that we're developing and that work maybe fairly robustly in the lab, how do those fail? And I think very little of that is known right now because very few of these really have made it out of the lab and into people's hands. And I think a lot of the big questions will be explored into sort of field use of these devices and where the sort of the major shortcomings are.
So thank you to both Aaron and Elliott and Marcia for moderating the session and introducing the speaker. I think this was a very exciting session, and I think what you guys are doing will help a lot of people. So thank you. I'll just want to announce that the next week, the theme for next week is design. And the speaker we will have is from Texas A&M Vinayak Krishnamurthy and Professor Jessica Menhol from Penn State. And the moderator for the session will be Professor Kristen Wood from University of Colorado, Denver. So I think it's going to be a very exciting presentation. So I hope to see you all next week. Thank you. And everyone can stay on and they can chat with the speakers. If you want to interact more, it will be open for another 20 minutes. Thank you.
Thanks again for creating this seminar series and inviting us to speak. I think this is a really special idea, especially right now where it's kind of hard to see people or get together otherwise. So I really enjoyed this and enjoyed this idea.
Thank you, Elliott.
I wanted to say hi to Elliott before I sign off.
Hey, good to see you.
Yeah, good to see you too, sort of. Still missing Eve, so I was hoping to get to see him sometime this summer, but. All right.
Video will be...
Elliott and Aaron. Really enjoyed them both. I'm sorry I had to do the last half from the carpool line, but I did have it all. I saw every slide.
Oh. Yes. Oh, man. Thank you, Marcia.
Thank you, Marcia.
Aaron and Elliott, let me, if you don't mind, hopefully now all the experts left, and so I could ask a silly question. So hopefully you can excuse me. There's one thing, I was watching your presentation, listening, very exciting, interesting, fascinating. But what struck me is that it was very what I call quote unquote mechanical. And I don't believe that's where the future of rehabilitation robotics is. I just don't. Old robotics machines, very mechanical parts. I mean, they're not built for humans. I mean, you build them for humans, you adopt them for humans. But is that really